how to read and interpret titration curves, okay? Now, this semester we've talked about a lot of graphs, a lot of curves, and usually I have a ton of questions about them. These, not as much. I mean, you're going to see these on the test, you're going to see these on the quiz, but it's not, there's not going to be like you're going to have a ton of questions about them. But there are a few things that we do need to know, okay? First of all, let's look at the axes, because that's where you should always start, looking at the x and the y when you are looking at these graphs, okay? So on the y, we have pH, okay? And on the x, we have volume of alkali added. Remember, alkali or alkaline is the word for base, okay? So as we add more volume of base, do you see how the pH is going up, okay? As you add more volume, again, volume of alkali added, pH over here, so all three of these graphs have the exact same axes. You can have titration curves that are volume of acid added, and what those would be is they'd start with a high pH, and as you add more acid, its pH would change accordingly. So it's going to have the same shape, but it's going to be almost reverse, okay? So we've got three different here, and I've got a fourth one on the board I'll talk about in a second. What you're going to need to be able to do is look at the graph and identify what type of titration is occurring. Is it a strong base and a weak acid? Is it a strong acid and a weak base? Or is it a strong acid with a strong base? That's what you're going to need to be able to do, okay? Now, do you remember that we learned the equivalence point is the point at which the moles of hydrogen equals the moles of hydroxide, okay? Or you could say the reaction is complete. All of the acid has reacted with all of the base to produce all salt and all water. It's not over, there's not too much base added, it's right, the perfect amount, okay? Now, these are neutralization reactions because we're adding an acid and a base to produce salt and water, okay? But do you remember how I told you, or the PowerPoint told you earlier, that it's really important that for us to know the equivalence point is not always neutral. Neutralization reactions do not mean it's going to be neutral at the end. So that's something you've got to get engraved in your brain. Neutralization reaction means acid plus base yields salt and water. Does not mean that it's going to have a neutral pH, a pH of 7 at the end. Let me give you an example. Not all salts are actually neutral, pH of 7. Bleach is a very famous base, and it's pretty toxic stuff. You have to be careful when you're dealing with bleach. But the reason why it has a pH basic, not because it is a base with hydroxide, it's actually a salt. Not all salts have a pH of 7. So if you're producing salts, you're not always going to end up neutral. It just depends on what salt you're producing. So let's look and see the main difference between these, okay? Let's look at the equivalence points. The equivalence point for a strong base and a weak acid is above 7. So do you see that's a basic pH? When we come over here, strong acid and weak base has a pH below 7 at the equivalence point. So if you've got a strong acid and a weak base, you're going to end up with an equivalence point pH that's actually acidic. If you've got a strong acid and a strong base, that's where you have exactly a pH of 7 at the equivalence point. Strong acid with strong base is going to be, of these three, the only one that's actually going to be neutral at the end, okay? Now, you should have been working on already learning and memorizing those strong acids and those strong bases as well as the weak acids and bases. So you should be able to look and see exactly which one would have equivalence point. If you've got a strong acid and a strong base, you're going to have a pH of 7 right at the equivalence point. So for my academic students, the best way to remember this is you've got a strong base with a weak acid. Think about which one's stronger, the base. So in the end, that's going to win out. Basic pH, because the base is stronger, okay? Whereas if you've got a strong acid with a weak base, that strong acid's going to win out, and in the end it's going to have an acidic pH. Let me show you, whereas this, before I move on over here, whereas this one is exactly neutral because they're both strong. One doesn't win over the other, okay? Now, some of you might be curious, what does a weak and weak look like? This is what a weak acid and a weak base looks like. Its equivalence point is at 7, but do you see how the titration curve is a lot more shallow, doesn't have as big of a dip here where the pH is changing drastically. It doesn't have that. It kind of stays the same throughout. It's because it behaves very much like a buffer. That's why it doesn't change its pH as you add more base as much, okay? You're not going to see this titration curve as often because it's not as common of a titration to actually complete. Typically, we do have at least one strong acid or base when we're completing titrations. Okay, now my academic folks, you can stop listening at this point. I just did want to talk to my honors class about one more concept, specifically why these two are actually have the pH above 7 here, pH below. Do you remember how we learned about conjugate acids and bases? Weak acids will produce a conjugate base. Okay? That means that it would be slightly basic on the product side. So if we have a strong base reacting with a weak acid, this weak acid is going to produce a conjugate base. That is actually why you have a basic pH in the end. Whereas if you have a weak base, it's going to produce a salt that's actually a conjugate acid. So why is bleach basic? Even though it doesn't have hydroxide on it, it's actually a basic because it's actually a weak base. And it could be produced from a titration. It could be produced from a neutralization reaction. So that's the actual real reason why we don't always end neutral at the end of a titration or at the end of a neutralization reaction. Okay, that's it for titration curves.